All right, well, let's get back to it. So we are following this tutorial to make a slimy broccoli shader in WebGL. And thus far, we have gotten to the point where we can start step one, where we have created an icosahedron sphere mesh in Elm. So let's move on. And I haven't actually read this tutorial, so you can read along with me. Let me bump up the font size a bit. So we'll need a shader. We'll need to, okay, and this is 3JS stuff. So we'll just have to interpret. Okay, so they're just telling you how to make shaders in 3JS, which we already know how to do in Elm. So here is our Vertex Shader, and this is taking a position which is coming from our vertex attributes, the model view matrix, and the projection matrix. So in our cube example, the role of this projection matrix is played by two things, the camera and the perspective. And the model view matrix is actually one I've been adding a new thing for. And then there's a separate matrix called rotation, which doesn't really need to be in there, but I've kind of left it just for demo purposes. So let's start with this refactoring that I do whenever I start from this code template. Is extracting a type alias for our uniforms. And our type alias uniforms equals this. And we're going to add in a new matrix called transform. Well, actually, we don't even need that right now. We're fine with these that we have. Okay, so then our vertex shader takes the vertex attributes and the uniforms, and it spits out the varyings. And I'm going to make a type alias for this as well. Cool. So let's see. So VUV, this is, I think, just played by the role of our color for the moment. We might, if we understand more about that later, we might change or add that. And our GL position, this is basically equivalent to what we have, except we have this extra rotation and we have two independent matrices for the projection. Okay. And this is their fragment shader. And I guess they're using a UV mapping where they pass the UV value. Okay, so we'll probably want to hook that up later. I guess that would mean we'll have to calculate the UV values in our mesh. And I'm not entirely sure how that should be done in the algorithm. So let's just move on for the moment. And if we run into problems with that, we may have to come back and figure out how to do UV mapping on this sphere. Okay, and our current fragment shader takes, this is the uniforms, and it also gets the varyings, and is just drawing the color that it's given. All right, cool. So let's make some noise. Now, great, onto the fun part. So we're going to distribute each vertex along the direction of its normal, which we also haven't calculated in our mesh, so we may need to go back and do that. Imagine there are lines that go from the center. Oh, actually, in this case, the normal is just the same as the point. for a sphere. Because the normal is just the vector that points out perpendicular to the surface at a given at the vertex. Okay. So if we make some longer and shorter, then we'll have an interesting mesh. Great. So we're going to push all these out by taking the original point and adding the normal times some noise distortion, which will be different for each point. Okay. And then we're going to use perlin noise, which, okay, just has kind of a smooth transition. And, okay, so they're going to be using this other WebGL noise thing, and what does this have in it? Hopefully these are shaders. Ah, okay, great. And does it say which one of these is what? No, it doesn't. Okay, so this is just some code that we can copy into our shaders. And these are all MIT licensed shaders. Great. Okay, and it says we're going to be using the classic noise 3D. So let's find that. Classic noise 3D is here. Okay, so we'll just be able to copy this. There are a lot of alternatives. Simplex, noise texture. Ah, okay. Great. So let's distribute the vertex. We want to multiply the normal by a scalar factor. The coordinates for the noise are based on the normal being modified, and the noise value is modified. Okay. And we could use different noise functions. And we're also going to do additional distortion, adding a factor based on a larger low-frequency noise to disturb the shape. Okay, that sounds cool. This is very important when working with noise functions. Okay. And it can be, what is this saying? This is achieved using some value that's the same for every frame. It can be an attribute or a uniform, but usually like to use the UV coordinates, the position, or the normal. Okay, I don't really understand that paragraph. In storing the noise as fake ambient occlusion factor, oh. Is this talking about coloring things different based on the depth? I'm not sure. Okay, so we're going to take the code from this noise generator and stick it into our Vertex Shader. Then there's going to be varyings. These are the outputs. Okay, so we're also going to send the noise out to the fragment shader so that the color can be based on the noise that was generated as well. Then turbulence, which takes the vector P, applies the noise. I'm assuming P noise is what's defined in here. There's C noise and P noise. Okay, cool. And then here's our main. So we're going to get a turbulence noise, then we're going to get another perlin noise, then combine those two together, then displace the vertex, and then do our camera projection. Okay, let's give this a try and see if we can get it to work. So I'm just going to copy this whole file from the noise. It'd be nice if we could save this in a variable and concatenate it, but I'm pretty sure that's not going to work in Elm. These GLSL things are special primitives in Elm. Okay, so there's all of our noise code. Then we already have these defined. Or no, the noise is a new one. So we're going to add a new varying. Then we have our turbulence function. Then we have this new code in our main. And then we're going to use new position here. Okay, and we have an Elm error because we added a new field to our varyings, which is called noise, and it's a float. So let's add that to our varyings here. Noise is a float. And what else is wrong? The shader, the type annotation for fragment shader. Okay, and I guess we have to add all the varyings here. Float noise. Cool. So that the Elm compiled, but it looks like we have some GL errors. The normal is undefined. Ah, great. Well, not great, but we can add the normal vector, or yeah, it is a vector. We'll add an attribute of vec3 called normal. And ooh, what happened here? Vec3, oh, attribute. I spelled attribute wrong. Okay, so now we have a new attribute called normal. We need to stick this in here, which is a vec3. And that means this is not correct. And actually, we can use the same point as the normal, or the same point on the sphere. Wow. Okay, well, we got something. Let me zoom the camera back out so we can see what we have here. And actually, I'm going to change the viewport size as well. So we'll make this 700 by 500. And we're also going to change the aspect ratio of the camera to be 3/2 to match the 750 by 500. And then let's zoom the camera farther out. Cool. So here is our perlin noise vertex shader. Great. Step 2. It doesn't quite look like what they have here. I'm noting. And that actually, if I remember correctly, is because they were using a sphere of radius 20, and we're using a sphere, I assume, of radius 1. So maybe we can multiply these. The second one is the color. So let's see. If we take all these and multiply it by 20, then we should end up with a sphere the size of the one they did. And that means the noise will have 20 times a smaller effect. Hey, Arpegachura. Yeah, welcome to the chat. Yeah, this is the first week I've been playing around with WebGL stuff, and not, from what I've seen, not a lot of people using Elm have played much with that, but it's pretty cool stuff that I've been getting to already. Okay, and I think this is not going to compile because we can't multiply a vec3 by number. but hopefully there is a function in here that will take a float. There we go, scale. So we're just going to say, instead of multiply, we're going to scale this. And it doesn't know which one because there's conflicting functions called that from different packages. So we want the math.vector3 scale function. And then we need to zoom our camera out much farther. Where did our camera go? Got a ton of code in here now. Camera. So let's zoom out to maybe 60. Yeah. There we go. So we have our icosahedron sphere deformed with perlin noise. And let's do the other thing they were doing, which is to change the... What are they doing here? They're taking the UV color position and multiplying it by something with the noise, and then adding a 0. Okay, so they're using the red-green components. They're mapping the UV to red-green components, so this would be for using a texture map later on. I think we can just calculate a color directly. So let's try to make our fragment shader a bit better. So shade is a uniform which just tells how bright to make it. And here we have our color. And let's just multiply for now our color by this same value that they were suggesting. Yeah, cool. So it kind of dims out in the holes. So now that we have that, I guess we can just give a constant color here instead of using different colors. So let's use our O.2, O.2, O.8. Uh-oh, we need a vector 3 here. Yeah, there we go. So we've got purple. I guess we should try to make this broccoli colored though. Let's look that up. Best broccoli color RGB values. Oh, there's a whole palette of broccoli color. Okay. Let's use the bright one. So 178 over 255, that's close enough to 0.7. So we'll use 0 for red, 0.7, or sure, we can use the whole value, 0.698, and the blue is 21, which is 0.082. 0.082. All right, so there's our broccoli knob. Well, I want to try real quick subdividing the sphere even farther. Where is that defined? That's here in our sphere mesh function, which is here. Okay, let's see what happens if we use 5 subdivisions. Cool. That seemed, I'm just going to leave it with that. I don't see any performance issues with doing that. Chroma.js is pretty great. I haven't heard of that before. What is, whoops. Oh, is that the site? No. Chroma.js. JavaScript library for color manipulations. Ah, cool. Oh, that's cool. Yeah, this would actually be a good library to port some of these features over to an Elm color library. That's cool. I will bookmark that. All right. So we now have our spinning broccoli knob. The next step is to animate this. And actually I want to bump up the brightness in our uniform. So let's make the shade 1.0. Get a bit more vibrant of a broccoli color. There we go. All right, and now for movement. I guess we skipped ahead and did the color already. All right. Oh yeah, so in this tutorial that we're reading, they actually use texture mapping and load like a slice of an image for their color palette. So I'm going to skip that part since we already have, in my opinion, a relatively nice color scheme going on. Does the tutorial get into masking? I don't think this one does. And I actually haven't heard about that before. Is that something available in WebGL or only in OpenGL? Yeah, so here's their example. They use like a sampled color palette from an explosion image. Oh, okay. So I guess I just skipped over all the code. So here we want the movement. And it looks like they are creating a value called f, which passes the time, and they're creating a texture called t. So I am going to skip the t part, and actually we already have a value called t that we pass to our uniforms. So I'm going to just set this to be, let's just call it time equals t, and we will add that to our uniforms. Time is a float. And how do they update it? They update it by, whoa, what are they doing? 00025 times how long the app has been running. Okay. I am not going to follow that. But what I am going to change is this from the template and make the t in our program correspond to seconds. So t will increase by 1 every second, and it's a float, so it'll increment smoothly. Okay, then they're adding their uniform called time to pull it out in their shader, in their Vertex Shader. I'm going to split these out. So this comes from the uniforms. Uniform float time. And what do they do with time? They add it here to the turbulence to animate the noise displacement. Okay. So the normal plus time. Whoa. That's crazy. So let's slow this down a little bit. Let's divide by maybe 4. That is pretty awesome, though. Oh, what happened here? Can we not divide by, oh, it must think it's an integer? Is that what's happening in C? Let's divide by 4.0. Yeah, there we go. Okay, we have to make it a float. Okay, and I'm also going to slow down the rotation because it increased when we changed the speed at which the t value increases in this program. So, actually, why don't we just turn off the rotation for now? This is just going to be identity matrix. And this is math.matrix4.identity. Yeah. It looks nice and smoky. Not really slimy like I was hoping for. let's see, is there a way we could modify kind of like the scale of the noise to make this look slimier? Not sure. If you have thoughts in the chat, let me know. Or Peggy Tura, I'm looking at you. And what did they do for the color? They're sampling a texture to make it look more natural. It also includes a random function to break the gradient a bit. Ah, interesting. Let's try adding this randomness to our fragment shader. And this gives us what? A random vector 3? Or, oh, no, I guess it gives us a float. And I'm not sure how does this random function work? Using a Voronoi pattern or another overlay? Actually, Evan was showing me yesterday, there's Elm Shader Toy, which is a project that this guy Kfish made. And I'll show this demo. Yeah, he has a Voronoi shader in this demo, and actually some other crazy whoops. How can I move this around? Yeah. This one over here is a Voronoi shader. Which I haven't looked at the code for that, but yeah, that'd be kind of cool. I don't think we have time to look into that today, though. But yeah, that's Kfish on GitHub. If you want to look at, like, these are the most sophisticated shaders I've seen anyone else do in Elm before I started trying to do this stuff this week. Actually, I'll keep that tab open so I remember to add it to the YouTube description. Oh, what's the website? Well, which website do you mean? The tutorial we're looking at? This is clicktorelease.com. Oh yeah, okay, so we were about to add noise, some random value, to our color. So why don't we add this to just like one of the components? Can we, what's the best way to do this? Can we take this and then add a vec4 to it? Plus, and then we'll make this like r, comma 0, comma 0, comma 0. Let's see what that does. That does not work. Random. There's no matching overloaded function. Did they pull in other... Oh, here we go. They pulled in this random, or they wrote this random function. And what is glfrag chord? I'm not sure what we're seeing. Let's try to make this noise more intense. Interesting. I am not sure I like that at all. But, okay, yeah, I'm just gonna take this noise out. And get rid of this. And, okay, we're back where we started with our exploding broccoli. Let's see. Let's experiment a little bit with changing the background color. And then I think that's going to be it. Actually, here's their slimy broccoli example from their tutorial, so we can compare. And there's this demo, interestingly, has some little artifacts you can see on some of the, like, seems to be right on the axes. So I don't know what's going on with that. Oh, interesting. They inverted the color scheme in their rendering. Okay, maybe we can have ours kind of be dark purple in the in parts and have a background. Okay, so I want to change the background, which we can change here, where we set the attributes that are put on the WebGL canvas element using HTML attributes.style. And give it a list, and I'll stick in, these are just CSS styles of, let's just use a dark gray, like 444. There we go. And then let's see. So how can we do a sliding scale between? Can we just add two vectors together and divide them? Let's add something to the uniform for the two colors that we're going to fade between. So let's add a uniform vec3, which is going to be color 1, and we'll add a color 2. And let's get that to compile first, and then we'll use those. Actually, so rather than vColor, oh, interesting. So maybe we do want one of the colors to come from the mesh. Yeah, let's do that. So we'll call this background color, and we'll fade between the color from the mesh and the background color. Okay, so that means we need to change our uniforms type. Uniforms, here we're going to add a background color field, which is a vector3, and we'll add it here. And I want to use a nice slimy purple color. Which one looks slimier? I think definitely this bright one, but I'm going to want it to be darker than this. So this is 148.021. 148, I'm just going to convert these to floats. So 0.578. And what, 21? 21.082. Okay, so that should compile again. Oh, it's a vector3. And now, I'm hoping we can make the real color. How do we define variables? We just put the type vec3 final color is going to equal the vertex color times, let's see, how is this going to work? We want to have a P, which is going to be a float between 0 and 1. So this is going to be this is going to go between 0 and 1, and then we'll take our V color and multiply it by P, and then add our background color and multiply it by P minus 1, or sorry, 1 minus P, and that should give us a weighted average of the two colors, with P being the weight. I'm hoping. And then we'll use final color. Let's see how that goes. Okay, I wrote some bad C code. Oh, I spelled final color wrong. And now what's going on here? Wrong operand type. No operand minus. Oh, I can't use an integer. I have to say 1.0 minus P. Silly C. Hey. Okay, so that is not the color I wanted. Why is it red? So let's for a moment just set P equal to 0. And this should be, 0.0, fine. So that's red, and I'm not sure where that red came from. Okay, so there's green. And let's see what the background color is. Maybe I got the background color wrong. Oh, okay. So yeah, this interpolation actually worked. I just have the wrong, I messed up converting this color. Oh, it's not 21, it's 200 and something. D3, 211. Okay, so 211 over 256 is 824. 0.824. All right, so there's our purple. It's not as dark as I would necessarily like, but that's okay. We can fix that in a second. And then final color. And there's our green. And now if we put the interpolation back based on the noise, we should have purple in the shadows. Yeah, nice. So then let's dim this down. So we'll say scale by 0.2 this vector and make it a much darker purple. What's wrong? Oh, I meant math.make vector3 dot scale. And that's super dark, maybe 0.4. Yeah, there we go. Now we're talking. And maybe we can zoom the camera in a little bit. And darken the background some more. And maybe make it a little purple. And maybe even darker. And yeah, let's try flipping these around. Actually, and have the purple be on the outside. That's like, what is the word? Supernatural broccoli rather than slimy. And okay, let's try playing also a little bit with the speed of this. So we could like slow this down to like 12. Yeah. And And let's see, so this extra noise is based on the position. Let's try creating another, let's see, so let's say noise plus equals. Can we say that? Yeah, background color is just the CSS attribute that we're applying to the HTML element that's containing the WebGL canvas. So let's see, if we do this, we're going to get the same thing, just multiplied. So what I'd like to do is have a much smaller noise that's added that's somewhat different. So we'd use the normal, that's fine. We'll offset this by some arbitrary amount so that we get a different phase of noise. Oh, 3.0, fine. And then we'll have this move at a much faster rate. Let's see what happens if we have this smaller noise go faster. I kind of see some rippling going on. Let's see what that second layer looks like on its own. Oh, fine, 0.0. To tell it when everything's afloat. Yeah, so I'd like this to be a much tighter noise. Can we do that by scaling the normal when we pass it to the turbulence function? Or, let's see, it was bigger. Let's try making this really large. Yeah, there we go. I don't know if you can see that very well, but the frequency of the noise is much higher now. So let's actually make this 6. 6.0, fine. I'm getting to hate C after this. I was thinking earlier today, it'd be great if there was a way to actually write your shaders in Elm somehow and have some way to define things in Elm that would get translated into C code for shaders. That would be a fun project if someone wants to do it. I don't really want to do that work, but if anyone makes such a thing, I would love to use it. Yeah. There we go. And I'm going to slow this one down, the low frequency noise, by a bit. Yeah. That is, I think that's pretty awesome. So, one of my friends told me to make a tentacle for today's Codevember. So I didn't get to that point. We'd have to write another algorithm to build a different mesh. Actually, I wonder if we can do that. Let's see. So what would it take to make a tentacle-shaped mesh? Yeah, I think I don't have time for that, because we could make a cylinder. To do that, we'd have to make circles of varying sizes, and then we would have to connect each ring with a strip of triangles. So we could probably do that with not too much time, but then I'd kind of want to add a way to have it deform or like curve rather than just being a straight cylinder, or a cone, I guess is what it would be called if it's tapering off. Cool. So I think I'm going to leave this here with what we have. And actually this, like yesterday, if you had asked me if I would be able to make something in Elm that looked like this, I would have said no. So I'm glad I came across this tutorial, and I'm glad it was relatively easy as well. And this is actually a really cool result. And I've been learning slowly that like people put a ton of code into the shaders. So like today we just copied this MIT licensed noise generator. But yeah, I've been looking at some other cool WebGL examples, and most of them just like put tons and tons of code into the shader and don't really have many meshes at all. So yeah, if anyone wants to get on building an Elm library that can compose shaders, that would be really cool. So, all right, well that's it for today. I'm not sure what my schedule is tomorrow. I will be doing another Codevember, and I expect I'll be streaming it. But I have no idea what yet again. I haven't had time to refill my ideas. Actually, I'll probably look on the Codevember hashtag on Twitter for some examples, and hopefully get some inspiration from that. So thanks for tuning in, everyone, and thanks for keeping me company in the chat as well. And yeah, especially if anyone makes some other cool WebGL stuff in Elm, share that shit. There haven't been many good examples, so I would love to see it myself. I'm sure other people would love to be inspired to experiment more with WebGL in Elm. So yeah, I will see you all next time, hopefully tomorrow. Bye.